In Chapter 8, the first thing we're going to talk about is exponential growth. So by the end of this lesson, you should be able to model exponential growth. So let's review what an exponential function is. So far we have only dealt with linear functions in this class. They've looked something like y equals 10x plus 2. This right here was our y-intercept. This is where we start. And this was our rate of change. And remember, we like to call that slope when we're talking about a linear function. So if I gave you a story like there was 2 people in a room, that's our y-intercept, and then it grew by 10 people every minute. You would add 10 people every time. That's our rate of change. Now an exponential function is a little different, and this kind of run on 2 lines, but it should be y equals a times b to the x. And now I know we have a b in this, just like we did in y equals mx plus b, but it means something different this time. This time the a is our y-intercept, or our starting point, and b is something called the growth factor. And this time it's a little different because our growth factor isn't adding every time, it's multiplying instead. So in this example, I want you to tell me what the growth factor is and where it crosses the y-axis, the y-intercept. So today we're going to focus on exponential growth, and tomorrow we'll talk about exponential decay. But growth is where the growth factor is greater than 1, where something is growing. So in this example here, our growth factor is 2. And because of that, that means things are getting twice as big every time. It's doubling. It goes from 3/4 to 1.5 to 3 to 6 to 12. And if we kept going, it would go to 24. It would keep doubling every time. And as you can see from this graph, exponential growth starts off really small, and then it shoots up. It gets really big really quick. So let's say in parts of the United States, wolves are being reintroduced to wilderness areas where they had become extinct. Suppose 20 wolves are released in northern Michigan, and the yearly growth factor is expected to be 1.2. Make a table showing the projected number of wolves at the end of each of the first 6 years. So if we have our x and our y, we start off with 20 wolves. After 1 year, it gets multiplied by 1.2. That's the growth factor. So we're going to take 20, multiply it by 1.2, and you end up with 24 wolves. And now we can keep going. 24 times 1.2 gives us 28.8. And since we can't have 0.8 wolves, let's round it to 29. And we could keep going literally all day. After 3 years, there's going to be about 35 wolves, because the growth factor goes up by 1.2. Now if you notice, we're not adding the same thing every time. This first one we went up by 4 and then 5 and then it jumps to 6, and this is kind of a coincidence that it goes up by 1 every time, but it's not the same thing like it would be with linear. So then let's write an equation. So remember, it's got to be in this form, y equals a times b to the x, because it's an exponential function. Remember that a is your starting point, so 20, and b is your growth factor, 1.2 to the x power. So now let's do one that's a little backwards. I'm going to give you a table, and you need to find the growth factor. So what we're looking for here is we have an elk population that starts off at 30, and in 1 year it jumps to 57. So we're trying to figure out, what did we multiply by to go from 30 to 57? What can we multiply 57 by to go from 57 to 108? So the opposite of multiplication is going to be division. That's what we're going to do. 57 divided by 30. If you divide that, you get exactly 1.9. And then we should check with some of the other ones. If we do 108 divided by 57, you end up with something close of 1.89. And then we could even do the next one, 206 divided by 108. And you get 1.91. So all of these are right around 1.9. We're going to say that 1.9 is our growth factor. So we can answer the next couple questions, but we're going to answer model order. Let's do C first. Write an equation you could use to predict the elk population for any year. So remember, it has to look like this. And our starting point was we started with 30 elk, and it's growing by 1.9 every year. So then we can use that to figure out how many elks there will be after 10 years. So all we got to do is plug it in. Y equals 30 times 1.9 to the 10th power. And then we have to remember PEMDAS. So we can't multiply 30 and 1.9 together and then take it to the 10th power. We have to do the exponent part first. So we have to do 1.9 to the 10th power, and then take that number, you get like 613, and multiply it by 30. So we end up with, after about 10 years, about 18,393 elk. We could do the same thing for 15, and you get a much bigger number. So let's do another problem. Maya's grandpa opened a savings account for her when she was born. He opened the account with $100 and didn't add or take out any money after that. The money in the account grows at a rate of 4% per year. Make a table to show the amount in the account from the time she was born to the time she turned 10. So when she was born, that's when the year was 0, it started with $100. Now the tricky part is here, for the next couple of years, it's growing at a rate of 4%. If you multiply 100 by 4%, you get 4. Our money didn't shrink, it grew by 4%. So what we have to remember is an exponential growth. A growth of 4% means that you have 100% of what you started with plus 4% more. Or when we put it in our problem, the growth factor means that we start with 1 of what we have, 100%, and then we added 4% more. So our growth factor is 1.04. So that's what we want to multiply by. And you end up with $104 the first time around. And then that $104 gets multiplied again by 1.04. And you end up with $108 the second year and 16 cents. And we keep multiplying it by 1.04. We could, again, fill this out all day long if we wanted to. But part B, what's the growth factor of the account? Remember, 4% is the growth rate. So the growth factor, what we would put in our equation, has to be 1.04. And then our actual equation, we need that growth factor, 1.04, but we also need how much it started with. So the starting value is $100. It grows 4% for every year. So there's our equation. Now with this comes something called compound interest. This is like a special type of story problem. So when a bank pays interest on the principal and the interest in the account, the bank is paying compound interest. An interest period is the length of time over which the interest is calculated. So this equation is very similar to y equals a times b to the x power. The a in this is our principal, or the initial investment, whatever you're putting in the bank account to start with. This is our y-intercept, just like before. Now this stuff inside of here is kind of what we did in this last problem. If I tell you that your bank is giving you 4% interest, we had to add 100% to that. So that's what this 1 is for, 1 plus my rate. And then this n that you see here is the number of times that your interest is compounded, which we'll talk about that in a second. But then the x up here is the number of times they're going to calculate interest. This is like our x. So when you have a bank and they tell you that your annual interest rate is 8%, that could mean several things. If they compound it annually, that means after every year, so 12 months have to go by, they look at whatever's in your bank account and they give you 8% on it. If something is compounded semi-annually, That means after 6 months, they look at what's in your bank account, they give you 4% of it, and then it lets another 6 months go by and they give you another 4%. So it's a total of 8%. If they do it quarterly, that means they look every 3 months, or they do it 4 times a year, and they give you 2% every time. If they do it monthly, that means they do it after 1 month, so they end up doing it 12 times, and they give you 8% divided by 12, or about 2/3% every month. So all of these eventually add to a total of 8%, but it makes sense to have things compounded more often, because that means that they're giving you a little bit of interest at a time, but then they use that interest as your new starting value, as your new principal amount. So the more that things are compounded, the more often you're going to get free money, basically. So this thing right here, this rate divided by the number of times it's compounded, is what this is talking about here. So let's do a problem. Suppose your parents deposited $1,500 in an account paying 3.5% interest compounded annually. So they only look at it once a year, and they only give you interest once a year. Find the account balance after 18 years. So let's write down what the equation is. If we go back here, your compound interest is your principal times 1 plus your rate divided by the number of times we compound it, to the number of times we compound it times the number of years. So the total amount that you're going to get is your principal, so your starting value, just like before. And then this 3.5%, just like the 4% that Maya's grandpa gave her, this is really 1.035. So we have to take that into account. And we're only going to compound this once. So the number of times we're going to split this up is only 1 time. And then we're going to take that to the power of 1 times 18, because they're only going to do it 18 times over those 18 years. So we can quickly simplify some of this stuff. And this looks exactly like the problem that Maya had. This whole compounded annually thing makes our life pretty easy. So this means that it grows at 3.5%, but we have to take into account that you have this initial amount, and then we're going to look at it for 18 years. So again, when you type this in your calculator, remember to follow PEMDAS, so 1.035 to the 18th power, and then you're going to multiply that by the 1,500. So you get $2,786.23. So after 18 years, you basically have an extra $1,200. It almost doubled that you just got because your bank paid you interest. Now the whole compounded thing, let's do the exact same problem, but let's say that it's compounded quarterly. So that means instead of doing it just 18 times once a year, that they do it 4 times a year for 18 years. So we're going to set up the equation, the rate divided by the number of times, and then to the nt power. So the amount that we're going to walk away with is our principal, what we start with, the 1,500, times 1 plus, it's still the same rate of 3.5%, but this time they're not going to give you 3.5% 4 times a year, because that would be 14%. They're going to give you 1/4 of it every time. And then instead of just doing it 18 times, they're going to do it 4 times a year for 18 years. So then we need to do some simplifying. So this stays the same for right now. And we get 1 plus 0.035 divided by 4 is 0.00875. And the power we want to take it to is the 72nd power. So if you notice from here to here, the exponent is way bigger, but the number to the exponent is way smaller. So just like before, when we want to type this in our calculator, make sure to follow PEMDAS. So do your exponent first to the 72nd power, and then multiply it by 1,500. So if it gets compounded quarterly, we end up making $2,800 and $8 and about 71 cents. So if we go to compare these, this was $27.86, and this one's $28.08. So if it's compounded quarterly, we get a little more of that free money that we didn't have to do anything with besides just let the bank hold on to it. So the compounding quarterly doesn't drastically change it, but it gives us about, I don't know, about 20, 30 bucks more for absolutely no work on our part. So you should be able to model exponential growth. Try doing this problem right here on your own, and then we can go over any questions you have in class. Have a good night.